Hi, welcome to Lesson 5 of Dynamics in Space for Motion Time Graph Part 3. We're looking today at velocity time and acceleration time graph. First of all, a quick starter. So if you pause the video at the moment and have a go at this. Right, we'll move on and have a look at the answers. This is basically a displacement time graph as you had last time. And we're trying to calculate the velocity during the first second and then the total distance travelled. Okay, the first part, to calculate the velocity during the first second. The velocity is the gradient of the graph in the first second. It doesn't actually change, so we're not going to have any issues there. So the gradient over the first second is given by 2 points. In this case, I have chosen as my final point 1, 2 here, the coordinates 1, 2, and my initial point 0, 0. That gives us the difference in the y's being 2 minus 0, and the difference in the x's being 1 minus 0, and an answer of 2 meters per second. The second part of the question was looking at the total distance travelled. Remember, the total distance is the sum of the distances in each section of the graph. So, in this case, the total distance is 2 plus 2 plus 2, which equals 6 meters. Remember, distances are always positive, even if the change in displacement is negative. Right, just a quick reminder, although we did this last time, that the displacement here, the change in the displacement here is plus 2, so that's basically a distance of 2 meters. The change in displacement here is minus 2, but that's still another distance of 2 meters, so it's like someone walking to the right for 2 meters and then walking back to the left for 2 meters. Remember, the change in the displacement gives you the distance and it gives you an idea of the direction of movement too. In this case, the person or the object is going 2 meters to the other side of the starting point. But that doesn't actually really matter here. It's still another 2 meters covered. Please go back to the previous lesson if you're not sure about any of these points, or ask questions at the bottom of the Google Classroom. Okay, today we're going to be learning to interpret velocity time graphs and acceleration time graphs and basically convert between the two and the success criteria given there. The first success criteria here is really revision of National 5. So slides 1 to 10 are really very similar to the first motion time graph lesson, and they're also revision of National 5 work, but it's probably worth reminding yourself of them anyway. Okay, this is obviously revision work that we've covered before. But velocity time graph obviously shows you the velocity of an object at any time, and because it's a vector, positive and negative values of velocity tell you whether the object is moving to one side or the other. So for instance, up here, when the velocity is positive, it tells you it must be moving one way, in one direction. So that could be to the left, or it could be to the right, depending what you decide positive is. It could be up, or it could be down. But no matter what, when it's below the axis here, when the values are negative, it has to be the opposite direction to what it's doing up here. So if upwards was to the right, if positive was to the right, then it means that this must be moving to the left here. The other thing we need to know is that changes in velocity tell you the direction of the acceleration. So this change here, the fact that the velocity is increasing or is becoming more positive, means that the acceleration is positive. When the velocity is becoming more negative here, the acceleration is negative. Velocity time graph shows you the velocity of an object at any given time. And the gradient of it, this is really just an extension of what we've just talked about there. The gradient shows you the rate that the velocity is changing each second. So it's called the acceleration. So if we can actually calculate the gradient of these sections, then we can work out the rate that the velocity is increasing by every second, and that will give us the acceleration. So this has a positive acceleration, this has a zero acceleration because there's no gradient, and this has a negative acceleration. One thing to note is at this point here, we'll look at this a little bit more in the next and last lesson on graphs, but this point here the velocity is zero, but there is still a gradient. The first worked example that we're going to look at here is really revision of National 5, so I'm going to go through it quite quickly. We also looked at it a couple of lessons ago in the first lesson of motion time graphs. We're looking for the object's acceleration after 0.5 seconds. Now, after 0.5 seconds, to get the acceleration, we need to know the gradient. The gradient to this point here is actually going to be the gradient of this entire straight line, because the gradient doesn't change. So the gradient at 0.5 seconds would be given by the normal gradient formula, where I'm using in this case a point at the end of the line and the beginning of the line, but any 2 points would do, and put them into the equation, that's what you get there. Again, what's the object's acceleration after 3.5 seconds? The reason I've put this in is because 3.5 seconds is actually is a point with a velocity 0. So at this point, the object would be momentarily stopped. Now that sometimes confuses people a bit, but the thing is, remember, if you go back and you really think about it, the acceleration is given by the gradient. Well, the gradient here hasn't gone to 0 just because the velocity has gone to 0. An object can momentarily stop, but actually is still accelerating. Again, we'll look at that a little bit more closely in the next lesson. So we have to calculate the gradient at that point, which is the gradient of the straight line at the end, and the 2 points I've chosen are the ones at the end, which is 4, -4, and 3, 4. And again, we just use some stuff from maths to work out the gradient. Wee reminder at the bottom, the gradient at 3.5 seconds is the gradient of the last straight line section, and just because the velocity is 0, it does not mean the gradient 0. It definitely isn't. The second part of this worked example is again revision of National 5 and revision of the very first lesson on motion time graphs at higher. What is the displacement after 4 seconds? Well, displacement is the area under the graph, and under again is in apostrophes, inverted commas, because we are looking at sometimes negative displacements that would really be kind of above the graph, I suppose. There are 4 areas here. And to make this a little bit easier, what I'm going to try and do is to kind of show you these 4 areas. So this is area 1 here, if I had to put that in. That would be area 1, would be the area under this triangle here. Okay? Area 2 would be really this area here, this rectangular area under the rectangle here. Area 3, if you excuse my really bad drawing, would be this area. Okay, this is new stuff at higher, and there's not a huge amount of it. Acceleration time graph. An acceleration time graph fairly obviously shows the acceleration of an object at any given time. So for instance, in the one that I've got here, for the first 1 second, the acceleration is at 3 meters per second, then it jumps instantly, and that's what this vertical line basically means. It's jumping instantly down to -1 meter per second for a further 2 seconds. Good news is, we don't look at the gradient of acceleration time graph, not at higher, even not at advanced higher. The area under an AT graph, though, we do need to know about, and it's basically, it gives you the velocity. So higher acceleration is always constant, and you're always going to get these kind of horizontal line graphs for acceleration. We don't deal at higher level with changing acceleration. So here's a worked example that might help you understand it a little bit better. We're trying to find out the velocity after 3 seconds here. Now the velocity is the area under the graph. And there are 2 areas here. The good news is they tend to be quite simple areas because they're all horizontal lines, they're always rectangles. So we've got area 1 here, and we have area 2 over here. Okay, so what are we going to do with this? Well, areas are quite simple, just as we've done before. 3 times 1 plus 2 times -1. Okay, remember, it's 2 seconds because 1 to 3 is 2 seconds, and it's -1 because we're going down by 1. Sometimes people like to set this out slightly differently, and they like to say. The second thing you need to be able to do at higher is to convert between the 2 types of graphs, velocity time and acceleration time. So the first wee example I'm going to show you here is going from velocity time to acceleration time. This is probably the most common example you're going to find at higher, and it comes up an awful lot. It's easiest if you think of an acceleration time graph as being a gradient time graph of the equivalent VT graph. So if you start off with the velocity time graph, and you're basically plotting the gradient of that graph against time, and that will get you your acceleration time graph. I've shown you both the question, so the velocity time graph, and the answer, the acceleration time graph together here, so you get a wee idea. One of the reasons I've done this is that quite often the acceleration time graphs look a bit strange, and they don't look like what you'd expect them to look like. It's really important when you're doing these questions that you do take it step by step. If you do this and you follow it through in a logical order, taking the steps one bit at a time, then you will get to the right answer. The intuitive solution, the one that looks the most obvious, is not always the correct one. So looking at these in order, we've got three sections in this graph. Between 0 and 1 seconds, between 1 and 3 seconds, and between 3 and 4 seconds. The first section, if you calculate the gradient of this, is 4. The gradient of this is 4, so therefore it's got a constant acceleration of 4 meters per second. How do I know it's constant? Well, it's a straight line. Straight velocity time graph line here at an angle, that means it's a constant acceleration. For the second section, the gradient is 0. It's going at a constant speed, which means that the acceleration is 0, so it goes right along the x-axis here. And then for the third section, if you pick 2 points at either end of the line and you calculate the gradient, because it's a constant gradient, even though it goes through velocity 0, that doesn't matter. The acceleration, the gradient equals -8, and therefore the acceleration is -8. Right? It's important when you're doing this that you do it section by section and that you're quite logical about it. Right? Sometimes there's confusion, but if you do it stepwise, step by step, then you should be okay. You could also be asked to convert from an acceleration time to a velocity time graph. It is quite rare this way, but in this case again, you break it down and you do it in sections. What are the initial and final velocities in each section? I think that's probably the most important thing, and I'd probably advise you to actually write them on the graph as you're going along. Okay, for this last example here, we're going to go the opposite way around. We're going to go from an acceleration time graph to a velocity time graph. And again, this looks incredibly difficult unless you actually break it down to sections. So in this case, we have three distinct sections. This section, and this section here. For the first section, between 0 and 1 seconds, the acceleration is 0, so the speed, or the velocity basically, does not change and stays at 0 meters per second. Okay? The reason we know that is because it starts from rest, the acceleration is 0, it's 0, so for the first second here, it's going to be 0. Then between 1 and 3 seconds, the velocity, it starts at 0, because that's where we finished the previous section at, and it's accelerating at 2 meters per second squared, for 2 seconds. Right, put the numbers into the equation, v equals u plus at, and you get the final velocity to be 4 meters per second. Another way of looking at it is we start with 0, and we're going up at 2 meters per second every second as we go 0, 2, 4. For the last section, again, you'll have to go through this again yourself, but we actually start off with a speed of 4. I think that's probably the bit that most people get confused with. We're starting with 4 because we finished the previous section at 4. So we start with 4, and we've got an acceleration of -5 meters per second for a second. So that means we're taking off 5 meters per second in that second, and we get to -1. But if you just put the numbers into the equation, then you get the final speed. Then, when we transfer these across onto this graph here, effectively what we're doing is we're transferring points on, because these are all straight lines between the points. We start at 0, we finish at 0 after 1 second. So that's 2 points. After 3 seconds, we have got to 4. That's the second box here. After a further second, at 4 seconds, we've got to -1. So that then gets plotted there. So if we do 1, 2, 3, 4, and then we join the dots, then we should get this graph here. At this stage, it's worth going to try the questions. Please refer back to these slides to help. Remember, there's a PDF version in the Google Classroom, and ask any questions in Google Classroom if you're not sure about any aspect of this work. Thank you.